In the increasingly explored vastness of the cosmos, one thing is certain. Besides planets, it is filled with countless stars. And one of them, the closest to us, the one that interests us the most, is full of incredible secrets and revelations. Introducing the Sun. It has been feared and also been a god to many civilizations. The Sun has inspired countless legends, as well as poems and songs. It has been the protagonist and antagonist of movies and documentaries. But what makes the Sun what it is? What fuel does it use to maintain that intense brightness? Are all stars like the Sun? To discover this and a bit more, let's dive into the king of stars alongside the technologies available today. In antiquity, the main civilizations maintained an esoteric relationship with the Sun, since those peoples already had knowledge about the importance of the bright star for life. It was also through constant observation and attention to periods of sun and rain that ancient civilizations began to master the techniques of agriculture and livestock and even architectural ideas, once they began to build in a way to take advantage of sunlight while being able to protect themselves from the heat it emitted. But the Sun was more than that. It represented one of the most important deities for those civilizations. The ancient Egyptians, for example, worshipped Ra, the sun god. Obviously, they didn't call it sun at that time, as this name came about much later. However, they believed Ra to be the creator and maintainer of the order of everything. In ancient Greece, the sun was the representation of the god Helios. The legend of Prometheus, according to the ancient Greek playwright Aeschylus, tells how the Titan brought fire to humans and also revealed techniques of agriculture and architecture to take advantage of sunlight. In the early days of India, the sun was worshipped as the god Indra, the god of the air, seasons, and firmament. The rains fall according to Indra's will, and he is the protector of warriors, nature, and one of the guardians of the world. In Babylon, the sun was associated with the god Shamash. The ancient civilizations of Mesoamerica, such as the Incas, Mayas, and Aztecs, also worshipped the sun as a god of great importance, especially in regards to agriculture and life. However, for quite some time now, thanks to the evolution of technologies in various areas of knowledge, such as physics, biology, astronomy, among others, humanity has come to better understand not only the importance and functions of the sun in relation to the planet and the life that has proliferated, and still proliferates, on it, but also its composition, behavior, and what can happen when care is not taken here below. We know that, in fact, the sun is not a god, but one of the gigantic celestial bodies, a star, and like everything we know, it had a beginning, is in full activity, but will also have an end. However, we will no longer be here when that end is, at least, close to happening. Until around the year 1500 AD. It was thought that the Earth was the center of the universe, or rather, the center of everything, since notions of outer space at that time were minimal and very limited compared to what we know today. However, the Polish astronomer and mathematician Nicholas Copernicus stepped out of his study room and proposed that the Sun, and not the Earth, was the center of the universe. This theory, known as heliocentrism, was formulated by Copernicus. In the 16th century, observations by Galileo Galilei in the following century confirmed this theory. Johannes Kepler also played a crucial role in proving the elliptical movement of the planets around the Sun. Before Copernicus's heliocentric theory, it was believed in geocentrism, which placed the Earth at the center of the universe. This model was first developed in the 18th century by Emmanuel Swedenborg and Immanuel Kant and Pierre-Simon Laplace. According to this model, the Sun and all other celestial bodies revolved around the Earth. The idea that the Earth was the center of the universe was widely accepted until Copernicus's discoveries. However, Copernicus's heliocentrism was also overthrown almost 3 centuries later. The idea that the Sun was a star dates back to 450 BC, when a pre-Socratic philosopher named Anaxagoras proposed this idea. To him, all those little colored dots in the night sky were like the Sun, only farther away. However, the stellar nature of the Sun was only widely accepted after the observations of the English astronomer William Herschel in the 19th century. Today, it is generally known that the Sun is a type of yellow dwarf star, and despite the suggestion of color, our mother star is white. We see it as yellow. but only due to the presence of countless particles in the atmosphere that, among other things, change the daytime sky color to blue, instead of showing it as it really is, which we see during the night. Dark. Interestingly, you've just discovered that you've been deceived all your life, seeing a yolk-colored sun and a sky clear of clouds, right? Well, this is precisely what scientific research aims to do, bring reality to us. Although it is not the center of the universe, it is the center of our solar system, and everything within this system's perimeter, called the heliosphere, revolves around the sun, and not the other way around. Recent studies have shown that the heliosphere acts as a shield, protecting the entire solar system against highly fast and energy-charged particles from interstellar events, like supernovas occurring throughout the universe. Studies using ultramodern computing have also shown that the solar system does not have a regular and standardized shape, as one might think. The bubble it generates is not perfectly circular or elliptical but takes on a shape more similar to a croissant. Until not so long ago, the idea of our system's shape was more oval, but in any case, it was imagined to be a gigantic area. The so-called solar wind, which are actually rays formed by particles that the sun emits, leaves the mother star and travels in all directions through the universe. However, this wind has a limit. It is not infinite. This limit is determined by an imaginary line called the heliopause, which signals the edges of the heliosphere. And from these edges, scientists believe, we enter an area called interstellar space, which comprises a certain void, but not completely, between one stellar system and another. This space is not completely empty, as it also houses various other types of particles and is a passage route for rogue celestial bodies and, who knows, dark matter. This is a myth that has been studied with much attention by scientific communities. Another quite interesting thing after studying astronomical distances is that the Sun is not far from us. Its distance of about 150 million kilometers from Earth, or 1 astronomical unit, is equivalent to only 8 minutes of light. This means that a single particle of light from the Sun takes 8 minutes and 20 seconds to collide against the Earth's surface. Yes, the image you see of the Sun at this exact moment is delayed. If something visible happens now on the solar surface, we will only see it 8 long minutes later. And believe it or not, despite not seeming like it, our mother star has a mass 332,900 times greater than that of Earth and a volume of 1,300,000 times larger. Times larger than our planet, meaning 1.3 million Earth-sized planets could fit inside the Sun. Knowledge about the Sun King advanced significantly after NASA launched the Solar Dynamics Observatory, SDO, in February 2010, equipped to send data related to the Sun's outer layer, the solar corona. With the mission to unravel the mysteries of solar variations that impact both life on Earth and our technological systems, the SDO embarked on studying the solar surface and its vibrant atmosphere, exploring a variety of electromagnetic wavelengths. NASA, by extending its gaze beyond the visible spectrum, managed to uncover previously hidden details, fundamental to our understanding of the Sun. One particular image was captured at a wavelength of 19.3 nanometers, revealing the light from the extreme ultraviolet region. By adjusting the wavelength to match a color temperature of 1 million Kelvin, the upper region of the solar corona becomes clearly visible. Intriguingly, the solar corona can be seen with the naked eye during rare moments, like during a total solar eclipse. When the moon perfectly aligns between the Earth and the Sun, that is, during a total eclipse, the bright central disk known as the photosphere is completely obscured, revealing a glowing exterior. Although this sight is breathtaking, the solar corona presents even more details in the image captured by the SDO, making it a valuable tool for scientific studies. As we explore deeper into the Sun's features just below the corona, we find points of intense brightness indicating events known as solar flares at a color temperature of 20 million Kelvin. To capture images of the coronal explosions, the SDO used an infrared camera, which accurately captures this invisible range of the spectrum but provides details with incredible precision. Regarding the explosions, NASA obtained quite interesting information with the SDO. During the events, the Sun emits an exacerbated amount of energy and magnetic radiation. The explosions go beyond what we could classify as terrifying. Once their jets reach altitudes of millions of kilometers, and are caused when magnetic fields cross, distort, and reorganize rapidly. This activity is created by the turbulent nature of the plasma within the Sun itself, from where the fields originate. However, it's not only solar flares that release radiation. Deep within the Sun, there are darker regions known as coronal holes, which are a fascinating spectacle to explore with the help of extreme ultraviolet light. Coronal holes are waves of cooler, less dense plasma that are magnetically open. This means that, unlike field lines that form closed circuits returning to the solar surface, these field lines extend outwards, crossing the solar system. These regions allow solar wind particles to escape more easily into space. When these solar winds are directed toward Earth and collide with our planet's magnetosphere, they result in the beautiful aurora lights that dance in the night sky of Earth's polar regions. The use of ultraviolet light allows us to have a much more detailed view of these fascinating features of the Sun's outer layers. Light from the non-visible spectrum is an incredible tool for observing the various features present in the Sun's outer layers, including solar filaments, also known as solar prominences, which are large loops of plasma that rise from the solar surface. These gigantic loops are so large that they make the Earth look like a small particle and can extend for hundreds of thousands of kilometers into space. They can form in just a day, but a stable prominence can remain in the solar corona for several months. When plasma is ejected from the Sun, it releases energy so intense that many of the particles are sent across the universe, effectively burning anything in their path. What saves planet Earth from being scorched are basically three elements. The atmosphere, which absorbs most of the solar radiation, including ultraviolet radiation, which is highly harmful. The magnetic field or magnetosphere, which plays a crucial role in protecting against charged particles emitted by the Sun during solar flares. Since these particles are deflected by Earth's magnetic field, which acts literally like a shield, and also the so-called Van Allen belts, which are zones of charged particles trapped by Earth's magnetic field. Even so, there's a limit to this protection. Historically, there are records that a solar storm was so strong that it affected electrical and navigation systems on Earth. The worst part is that there are predictions for a new and alarming occurrence like this one, which could bring harmful consequences to humanity, especially because nowadays we make use of technologies tied to each other, such as satellites and GPS systems, cell phones, TV broadcasts. All of this, everything could be negatively affected by one of these storms and even cause a technological blackout. Now imagine nowadays being a month without being able to use your cell phone or turn on the TV. Returning to the matter of the plasma explosion, normally, when it happens, there's also rain on the surface of the Sun. But don't worry, because it's not H2O or water. The fact is that not all particles are launched into space in the explosion. A significant portion of them returns to the Sun in the form of rain. Indeed, on the Sun, the rain that shines brighter than gold is made of plasma. Definitely a quite different phenomenon and very beautiful to observe, but only from the distance we are from the Sun King, and even then with very specific special equipment such as space telescopes and some radio telescopes present on the Earth's surface. Scientists have named this phenomenon of the returning plasma to space as rain only to make things easier to understand. But it has nothing to do with the rain we know here, okay? On Earth, the water that falls from the sky is the same that evaporates from the surface and forms loaded clouds. Or joins others already formed to then be launched to the surface, but because of gravity, not because the cloud or the Earth ejected that water by pressure. The plasma rain, which returns gently to the solar surface, comes from the surface itself, when disturbances occur in it that, like a volcano, launch gases and dust upwards, in the case of the Sun, the plasma itself. The heavier plasma particles end up returning in the form of rain. By the way, a type of rain that would be impossible to come closer than what the Stonos showed with its images. Solar storms happen frequently, but they are usually minor and do not disturb the Earth's magnetosphere. However, every 11 years or so, for a period of time, the disturbances become much stronger and more frequent, giving rise to storms. This solar period is called the solar cycle, and we are currently going through it, so much so that there are predictions of a possible blackout in 2024, originated by the solar activities that are more active this year. There is still much to be discovered. Just as visible and ultraviolet light reveals different aspects when observing the same object, the use of two distinct wavelengths of non-visible light can be equally enlightening. To illustrate this, consider two images of the solar corona, captured at the same time interval, but using two different wavelengths. The first image, captured at a color temperature of 600,000 Kelvin, depicts the quiet corona and its coronal loops. The second, captured at a color temperature of 2 million Kelvin, reveals the active and much hotter regions of the corona. The comparison between the two images highlights the importance of varied approaches when investigating the star. What may initially appear as a single solar phenomenon may reveal itself as a complex and interconnected chain of events. We technically cannot cross the Sun's atmosphere yet. Going deeper, let's examine another image produced by the SDO, this time using a 160 nanometer wavelength of light, focusing on the transition region. This region is a layer that lies between the solar corona and the chromosphere, the lowest layer of the solar atmosphere, with a thickness of only about 100 kilometers. In this region, the Sun's thermal temperature dramatically increases from about 8,000 to 500,000 Kelvin. For an earthly comparison, the fiery lava that emerges from Kilauea in Hawaii has a temperature of 1,170 degrees Celsius, or 1,443 Kelvin. The temperature at the lower and deeper end of the transition region is almost 6 times hotter than that. At the upper end of the transition region, the temperature is 346 times hotter. A little deeper, and we reach the chromosphere, the last atmospheric layer before the solar surface. Here, we find spicules, jets of plasma that shoot from the solar surface at impressive speeds and can reach almost 10 kilometers in length. These spicules form and disappear in about 5 to 10 minutes. In 2017, scientists discovered that spicules are related to neutral particles, which give magnetically charged particles the buoyancy needed to escape the solar plasma. Going even deeper, we reach the photosphere, the Sun's surface. The photosphere, best viewed using visible light, is not the Sun's fixed and solid limit but rather a layer of plasma, the fourth state of matter. This layer is about 400 kilometers thick and is the deepest layer of the star that scientists can directly measure. Observing the Sun more closely, we notice dark spots on the left side, known as sunspots. They are cooler and, therefore, darker than the rest of the solar photosphere. Sunspots form where magnetic fields are strong, trapping heat below the photosphere. A comparison with a previous image of the Sun reveals a connection between sunspots and solar flares. Examining similar sunspots captured by the Swedish Solar Telescope using visible light, we notice irregular cells in the photosphere, similar to cooling and cracking lava. These cells, known as solar granules, are about 1,000 kilometers wide and represent the top layer of a turbulent convection cell below. The brighter areas within each granule indicate the hot fluid rising to the surface of the Sun. After cooling, the fluid sinks back down, repeating the cycle. This process is similar to the convection currents in the Earth's mantle that drive tectonic plates. Although, on average, it is estimated that each granule lasts only 20 minutes, the flow within the cells reaches supersonic speeds of more than 7 km per second, generating waves on the surface of the Sun due to sonic booms. Interestingly, these granules can also be seen in the full disk visualization of the Sun, using the same wavelength of visible light. What in the granulated image of the Sun appears to be the result of low resolution, are actually granules from the photosphere. Our solar exploration, for now, reaches its final destination. Perhaps in the not-so-distant future, science will find ways to delve even further into the solar organism and bring intriguing and real novelties from our mother star. Thank you for watching, and until next time.